Welcome to the next video in the Systems Programming video series. We're talking through the textbook Dive into Systems and moving on to section 4.8, discussing so-called real numbers in binary. Honestly, I think we're going to be talking about floating point numbers, which maybe already kind of gives you a better sense of what is going to be in this video. I think talking about real numbers is a little, at least to a mathematician, misguided, because what separates the real numbers from the rational numbers, I think a floating point number is better described as a model for some of the rational numbers. If you say the real numbers, then you almost necessarily have in mind infinite digit sequences. That's kind of what distinguishes the real numbers from the rational numbers, is that the real numbers permit literally any possible sequence of infinite digits. Whereas the rational numbers, at least in a certain kind of sense, have a more constrained definition. One version of its definition is that it has repeating decimal binary digit expansions, whether it doesn't matter what base you're in. So whatever, however you choose to think about it, I would call this a model of rational numbers, but here they call it a model of real numbers. But in any case, let's think about how we could simulate, or not simulate, but actually reproduce the whole idea of decimals with a decimal point and numbers that come after the decimal point, which we know are supposed to represent like fractional values or something like that. How could we do that in binary? Well, the logic is exactly the same, right? So if you had 1.23 in decimal, then this is the same as 1 times 10 to the 0, because anything in the position immediately to the left of the decimal is the units place, which is, the same as multiplying, right? Like it's just a single value, right? In some sense, right? So 10 to the 0, as we're somewhat familiar with. In fact, maybe it makes even more sense to give an example like 12.34. And then we could say that this is 1 times 10 to the 1 plus 2 times 10 to the 0. I think that makes sense, right? And then plus, right, to capture the decimal, right, the values after the decimal point, then you would say that's 3 times 10 to the negative 1, which is 3/10. And I think we're typically pretty familiar with that logic. So then plus 4 times 10 to the negative 2, which is, 4 over 100, if you like, or 0.04. So that's that's like the familiar system. So now what if we did it in binary, so that we said something like 11.01011, for instance. Okay, the stuff to the left of the dot is interpreted in the familiar way of 1 times 2 to the 1 plus 1 times 2 to the 0. Now, what about the stuff after the point? Well, that's going to be 0 times 2 to the negative 1 plus 1 times 2 to the negative 2 plus 0 times 2 to the negative 3, 1 times 2 to the negative 4, 1 times 2 to the negative 5. Okay, so the logic of the system is very much the same, of course, just constraining ourselves to using only the digits 0 and 1 and using the base of the exponent 2. So if we were to convert this to our familiar numbers, then we would say that this is 2 plus 1 plus 0 plus, 1/4 plus 0 plus 1/16 plus 1/32. And then if you want, you can go ahead and simplify this in your favorite way, whether that's as a decimal or as a fraction or whatever. But from here, we know where this is going. We know how this is going to turn into one kind of a simplified value that we're used to. And that's how you convert from a binary fractional value written with the dot notation over to something written in decimal notation. And of course, it is possible to convert the other way around, right? So we just converted from here to there, but it is just as possible to take any given number and find its digit sequence in binary. But that may or may not be the most interesting thing, so I'm not necessarily going to go through that. But I just want to establish these ideas. Now, how do we represent these things in hardware? Well, the book starts talking about a fixed point representation of these binary digit sequences. It talks about this fixed point. So what you could imagine is that we will just agree to reserve some sequence, right? Some places in memory, and have some sequence of bits, and there may be some understood by us, not represented in physical hardware, but understood by us, binary point, kind of, the binary version of a decimal point. And then maybe a few more addresses in memory, and each one of these, right, a 1 here represents just the value 1, whereas a 0 would represent 0. A 1 here would represent 2. A 1 here would represent 4, and so on. This is the reading to the left is the familiar binary system for integers. And then to the right is the system that we just introduced. And basically the idea is that this is a fixed point system, meaning that we all know and agree to where the decimal or the binary point is located, so that we know how to read numbers in this system. But what that means is that we have to all agree on where the binary point goes. Does it go here, or could it go there? I mean, it depends, do you want big numbers or do you want precise numbers, right? Because the more bits you reserve to the right of the binary point, the more precision you can get, right? The more finely you can control which number you're talking about. But the more bits you leave on the left side, the bigger you can make your numbers. And so which one do you want? Well, different people in different settings are going to have different values. And, so there are maybe a number of resolutions of this idea. But not only is that a problem, but the book, walks you through a certain amount of consideration and calculation showing that there are even other downsides to this system of representing binary fractional values. And it comes down to issues of error and accuracy and predicting the results of certain computations. So this is an undesirable system, this fixed point system. So we are going to instead replace it with a floating point system, which is where the name of the data structure float comes from. Now, to introduce this, the book has a perfectly good introduction to the idea, but I want to try a slightly different introduction, which is to imagine that you start from some digit sequence, right? And so I'm just going to write down a random digit sequence that could eventually become a binary number. So let's say 111010001. If we don't have any idea where the binary point goes, then we don't even know how to think about this as a number, right? If you can place the binary point there and now think about it as a number, but the fact that you could also place the binary point there could make it a very different number. And so if you don't know where the binary point is, you don't know which number it is. By the way, those aren't the only options. You could also have spaces here and put the binary point all the way out here, right? So that's a possibility for the location of the binary point. And not only on the right side, but also on the left side, you could place a binary point out here. And then implicitly, these values, and by the way, just to make sure that was clear, when you place the binary point in an extra position off to the right, we implicitly fill the empty spaces with zeros. Well, likewise, on the left-hand side, we could move the decimal place beyond the sequence of digits and locate a binary point out there and implicitly fill all the empty positions in the number with zeros. And this I guess I should maybe, point out that as you move the decimal around, just think about the number 1, or let's just say the sequence of decimal digits, 1, 2, 3, which if you place the decimal here is 123. If you place the decimal here, it's 12.3. And the conversion between the two is just a multiply or divide by 10. And likewise up here, pushing the decimal around to different locations is really just the same idea as multiplying or dividing by 2. So that's, an initial idea about like how these binary points work when you have some fixed digit sequence, right? So for a fixed digit sequence, if we could take that fixed digit sequence together with some data that specifies where we're going to locate the binary point. So we have a digit sequence, but then separately a bit of memory that will tell us where to place the binary point. Now we can start reading this as some non-negative number. And in a minute, we'll talk about also how to introduce the negatives. But for now, let's focus on the non-negative numbers. Now notice that if you have any digit sequence other than all zeros, it must have a leading one. So in this example, the leading one was this one right here. But, we could just as well have written it with its leading zeros out here, but that just seems like a waste of writing. Why write the extra zeros if you don't need them? So since we know that any number other than 0 will have some leading one, and as long as you know basically the sequence of digits, since the leading one is almost not needed, right, to specify what number you're talking about. If we just assume that there is always a leading one and the entire rest of the conversation is about what is the remaining digit sequence, right? So, the idea is we can just save ourselves a little bit of space in memory, right? We can basically not bother to write that leading one because we know that, it should be there for any number other than 0, and we'll specially code 0. But what we're going to do is we're going to leave this one implicit, right? We're not actually going to store that one in hardware because for almost every number, it's assumed to be there. And so to some degree, what this is starting to demonstrate a little bit is that there's going to be this mismatch between the bits that are stored in memory and where they are supposed to correspond in the sort of binary representation of the number, right? So we might not even be writing these zeros in memory because maybe they go beyond the space used to store the digit sequence, and we might not write these bits, and we also won't write this. So there's like a lot of things that are in the mathematical number which will not actually get written into a corresponding place in memory. So there's going to be this weaker correspondence between what is saved in memory and exactly how it translates, to a sequence of symbols written mathematically, right? That these are going to come apart a little bit. For the remainder of the conversation, let's not use so many digits or bits because, let's keep these examples small. So let's say that we just have 2 bits, and I'm going to focus on the digit sequence 0, 1. So that's 2 bits, and implicitly, there's always this leading 1, so really it's 1, 0, 1, right? Let's talk about this sequence of binary digits with the leading 1 being implicit so that what we're ultimately going to store in memory is only the 0, 1. And let's have separate pictures for the number that it represents as well as the thing that is actually stored in memory, right? So over here, I'm going to talk about what is stored in memory. And over here, I want to have even a further breakdown of the number as we would understand it in decimal versus the number as we would understand it in binary. So let's assume that by default, right, that you could make this, right, there are a variety of choices. Different people have made different choices about where we assume the default position is in a binary point, right? So let's just, for the sake of just inventing a totally small, fictitious, random example, just for illustrative purposes, let's assume that the binary point by default, actually, let's not put it there. Let's put the binary point by default over here, one position to the left of the implicit leading 1. So if in memory what I write is 0, 0, and these are going to be 2 bits that I reserve for myself to control the location of the binary point. So 0, 0 is telling me that I just put the binary point in its standard location, which we will just agree is 4 digits to the left, basically. Now, I also store in memory what the digit sequence is after the leading one, so I'm also going to store into memory 0, 1 in this example. So the amount of memory that I'm going to use throughout this example is I'm going to use 4 bits. 2 bits to control the location of the binary point, and another 2 bits to store the digit sequence after the leading one. And then let's think about all of the different numbers that could be represented in this system. So if we did it just with this default, right, like just with not moving the decimal from its default location, and here using this digit sequence with an implicit 1 to the left of that, then this would be as a binary number, we would write this as 0.0101. And then what is that in decimal? So that would be 1/4 plus 1/8 plus 1. Did I make a mistake previously in describing some of this? Oh no, that's fine. Yeah, the 1/8 place is correctly identified as 0 there. Okay, anyway. 0 instances of 1/2, 1 instance of 1/4, 0 instances of 1/8, 1 instance of 1/16. So this would be this. Okay, so that's how to understand this number. This is in, let's say, decimal. Now I'm not actually writing a decimal point, but still this is in decimal because I'm using digits 0 through 9. This is in binary, and this is the data stored in memory. Now let's do it, but this time let's see what happens if I change the thing that controls the location, right, like where we intend for the point to be located. So if I put a 1 here, we take that to mean that the decimal place is located 1 further to the right, or if you like, that means the same thing as multiplying by 2, right? Taking the base interpreted number and multiplying that by 2. But I'm going to keep the same digit sequence, right, because it's still going to be 1, 0, 1. So I'm still going to save 0, 1, and the leading one is implied. And now what number is this? Well, it is simply 0.101. And what this means is 1/2 plus 0 instances of 1/4 and then 1 instance of 1. Okay, and that's basically the same as multiplying by 2. And then now that I think maybe the picture is somewhat clear about like where this is going, the next thing that we could have if we incremented the thing controlling the decimal is we could have this, and that would actually represent the number 1.01, and that would be 2 plus 1/4. And then we could have 1, 1, 0, 1, that represents 1, 0.1, and that is 4 plus 1/2. And so this is going to be, right, this is just a very small toy example of the basic idea of floating point numbers, is that you're going to use some amount of data to control where the decimal place is, and in order to do that, you're going to have some idea of like a default location of the decimal place, which you can then shift from by manipulating or choosing different values to go in this location in memory. So you have a default location of the binary point. You can move it using a certain amount of data. And notice, by the way, that like if this is my system where my default is here and I give myself only 2 bits to control the location of the binary point, then the most I can move my binary point, right? I could move it 1, 2, 3, 4 times. And therefore, with an implied 1 and 2 further bits, I can basically place a decimal here. And then what I'm getting at is what is the biggest value that you could possibly store? Well, if you set everything to 1, like in memory you had 1111, right? This is going to be the biggest possible value that you could store in this system, and it is going to get interpreted as, as if the decimal place were located right here. And then this is going to be what? So a sequence of all ones, that the easiest way to think about that is that if you did one more, you would get a 1 with 4 zeros. That's the same thing as 2 to the 4. That's 16. So this must be the number 15, right? So this is 15. If that's in base 2, then this is the same as the number 15. So that's right. So in this system, putting the decimal by default where I put it, and giving myself this much memory to control the location of the binary point, then the biggest value I could possibly represent is 15. It is worth noting that in this particular system, we cannot even represent the number 0, right? Right, that's an issue for my small toy example. We will fix that when we get to the serious version of exactly how binary fractional values are actually stored using the usual system. It will be possible to represent the number 0. But in my system, as I have designed it here, because of this implied 1, there is no way to represent the number 0. You can represent a very small value. It's actually worth asking, what is the smallest value that this toy system could possibly represent? That would come from setting every single value to 0. So if we did set every single value to 0, like what if you had in memory 0, 0, 0, 0? Well, this would say that I do not shift my binary point off from its default location. So it would be here with a blank, an implied 1, because of how we're saying that everything here has an implied 1, then I have to have my implied 1 followed by the explicit sequence of 0, 0. This is the smallest number that my toy system could possibly represent. That's read in base 2. In our decimal system, that would be the number 1/4, this being filled implicitly by a 0. So in my toy system, the biggest number I can represent is 15. The smallest number that I can represent is a 4th. Okay, this is the base, right? So although I have not told you the serious system that is going to come here, this is actually how things are represented, and it uses a lot more data, a lot more space, both for this thing is going to control the location of the the binary point. This thing is going to control the sequence of bits other than the implied 1, which is there, right? That's the implied 1 in their system, the normal system. And we're also going to have a single sign bit so that we are able to represent negative numbers. But basically, right, this more, I guess, robust or full system with lots more space and also a sign bit is just a more realistic, more useful, bigger version of exactly what I described over here using a small number of bits. It's nice to see just how much data is allocated for each of the things, right? In my system, I had 2 bits to control the location of the binary point and 2 bits for the digit sequence. That is, right, they are not the same here, right? So you have, 23 bits. 23 bits here called the significand. And so the significand is abbreviated with just S here. And there are 23 bits to specify the significand, okay? The significand is what goes after the implied 1. So in my little toy system, the significand was those 2 bits at the rightmost end. But in the real system, there are 23 of them. Now, over here is where we control the location of the binary point. We call them the exponent bits. We abbreviate them with E. And how many of these are there? Well, 30 minus 23 is 7, so plus 1 because, right, of, whatever that phenomenon is where, like, you subtract the 2 endpoints, but you need to add 1 to correct for, I think it's called, like, the fence post problem or trick, or I don't know, something like that. Fence post something, I think. Anyway, but the point is 30 minus 23 plus 1 is 8, so we reserve 8 bits to specify the exponent, and then we reserve a final single bit for the sign. Still, as described, there is no way to represent the number 0. We'll get back to that in a minute. But this is the real sort of normal system. And the interpretation for almost any values that you put in any of these bits, for most of the time, almost every number is interpreted in the following way. Of course, the sign bit is basically like multiplying by -1 to the n, where n is whatever the sign bit is. So what that means is that if n is equal to 0, then this is -1 to the 0, which is equal to 1, which means that it's positive, right? It basically like wipes out the negative if this bit is set to 0. So 0 is what we use in that sign bit for positive numbers. And with a 1, -1 to the 1 is -1, and that makes the whole number negative. Okay, so basically, long story short, the sign bit set to 0 is positive, the sign bit set to 1 is negative. And it shows up in the formula like that. You can see here, what if we set all of our exponent bits to 0 just to see where, in a sense, the default or base location of the binary point is? Well, if you set all of them to 0, then this would read like the number 0. And the way we're supposed to interpret that, reading like the number 0, is that this value of e right here would be 0, meaning that this whole number, 2 to the e minus 27, that would be 2 to the negative 27 if we're setting e equal to 0. So what that means is move your decimal place, right? If you imagine that you are starting kind of from the units place, right, where like, say like this point right there would be the units value 0. But if we multiply by 2 to the negative 127, then you would move 1, 2, 3, and so on until you have moved 127 times. And that is the default location of the binary point in this system. If you had a sequence of all zeros in your exponent bits, then the decimal place would be located 127 places to the left of the units position or something like that. So that tells you, right, this 127 is basically telling you what this system takes to be the default location of the binary point. And then you can control it by incrementing e, right? Actually, it's worth thinking, what is the maximum value that e could possibly have? What if we filled this with a sequence of all ones? You would have 8 ones. And if you have 8 ones, then that is basically 2 to the 8 minus 1, right? Using a sort of logic and a math that we've seen a couple times now. So that would basically be the same thing as if you took 2 to the 8 and subtract by 1. What is 2 to the 8? I think that's what, like 256, I think, off the top of my head. And then you go down by 1, so 255. So the biggest number that e could be is, let's say, 255. And then if you put 255 here, 255 minus 127, oh, what is that? Let's scratch that out real quick. So 255 minus 127. So what? That's going to be a 4, so 128. And so what that means is that the largest thing that, right, like if you put e, if e is set by making all of these equal to 1, then this exponent up here will now have the value of 128, which basically means sending the decimal point 128 positions out to here. You can either slide your decimal point in this system, you can, by setting all of the exponent bits to 0, that essentially corresponds to locating the decimal point 127 places to the left of the units position, or in the other direction, setting everything to 1. Right? So this was setting everything to 0 to the left, and then setting everything to 1 is moving this 128 places to the right. So that's your right. That this system offers you that range of possibilities for where you can set the binary point. Okay, and then this is the digit sequence. I think I've already said that, like, just as I had a digit sequence here, which was, supposed to be this part of the number, there's always this implied 1 in front of it. That's what this is right here. So I don't know, do I need to explain that anymore? I'm not sure what else I could say about that. I hope that's clear. Yeah, I guess, right, and I guess as a matter of nomenclature, we've been calling them the significand, the exponent, the sign. That's all very standard. The significand is also sometimes called the mantissa, so just know that that alternate nomenclature is out there and common. There's the exponent. 127 is called the bias. So what I've been saying maybe is like the default location is actually more often described as the bias of this particular system. So 127 is the bias, whereas I was calling it, 127 places to the left was like the default. But, as long as you know the words and you know what they mean, doesn't really matter what we call them. Okay. And then there's the sign bit. Now it looks to me like this book, as far as I can tell, I'm not seeing how this could ever represent the number 0. That I think is usually described most of the time when describing how floating point values work. So we probably ought to just address that briefly. Basically, this interpretation is the interpretation almost all the time. But typically, we do reserve a few bit sequences to not be interpreted this way. Specifically, I can't, now I have to remember them off the top of my head. I could go Google them. I guess you could look them up if you're very interested. But it is possible to represent true 0 in this system because we would take a sequence of all zeros from the beginning to the end. I believe, if I recall correctly, and I am doing this off of the top of my head, having not looked at it for a while, I believe if we took the whole thing to be nothing but a sequence of all zeros, we actually would not, in that special carved out case, the computer would recognize that as a special case, not using this interpretation, but that would instead get read as 0. I believe there are a few other special carve-outs. I think in this, the standard for this, right, this whole system laid out here is called this IEEE. And I believe in this system, there are a few other carve-outs as well. One is meant to represent not a number, I think. Maybe another one is meant to represent positive infinity and negative infinity and so on. So this is the interpretation for almost every bit sequence, but there are a few bit sequences that the computer knows to reserve as not interpreted this way, but instead interpreted in some other special way. And by the way, because of these ways of making a couple exceptions, the number 0 is not actually represented in two ways, right? What you could think is that if you have some way of representing the number 0 and you have a sign bit, doesn't that mean that you're going to be forced to have a representation of positive 0 and negative 0 or something like that? And it turns out, no, because we make these special reserved sequences that get an alternate interpretation not like this, then therefore there is actually only one representation of the number 0. It adds to the complexity of the whole system, but it is better than not having it.